Of course, you first have to give your credit card so the money person is gone.
Yeah, exactly. That's right.
But anyway, so that's not a forward figure. But then I also have taxi book and
Yeah.
all.
That's one of the
Have a hotel for tonight and
I'd end up with Daniel at this place.
if worst comes to worst, I can also check where the bridges are.
Yeah, by the way, I got the email yesterday from Quanta from board. They put together the phase change model.
Okay.
They got a running version also in 3D as far as I see.
Okay, good.
Yes.
Great.
It's only quite a busy week.
Yeah, next week also.
Yeah.
So it is.
All right. Somebody going?
Also, I think I got to lift in a 3 week or something. That was my doctor's appointment in 2020.
Okay.
340.
Hello. Good to see you.
That's right. I think I'm gonna be interested if you guys have played them out. What that is.
I would just ask you for the key because then I think I need the information for the
Yeah. Yes, we got that.
that's good. I have a doctor's appointment as a portion big in the one from I have real okay, think about
Hey,
That's good.
And breakfast at days. From your inside. That was the most. You feel quick again, excellent. Excellent. So it's not 2 minutes. You'll give it another minute or so and then get started. Hey, to tell a private story, I just got half an hour ago the message that my flight back home tonight is cancelled. This is the third time in a row that this happens. Right.
Which eye?
Lufthansa. Yeah. So, twice the plane was there, but broke, so they couldn't fly, so they had to get something repaired. And today, obviously, the incoming flight is.
Yeah, I think the reliability of planes in Australia are going down as well. I was on one the other day. We took off, and then half an hour for the flight, they're like, "Yeah, we can't get our landing gear up. We have to turn around." And we're like, "What?"
Well, better not to get it up.
Yeah,
Get it done.
that is.
It's like if you are in Russia, I heard that they have no fare for the plane. So for example, the time they are using it for it's very dangerous. The place using the same because normally you have to change it after 400 hours. You have to change the time. If they don't get the more tire precious.
Oh, no tires.
Good tire from the.
By the way, can you see how many people are connected on the page so that we have an idea how many?
It's a wide interest seminar.
Yeah, I mean, I think on WebEx 4, 8, maybe 7.
Could be more because not all are shown here.
Yeah.
Anyway, don't mess up your screen. So really. And then there's also the YouTube channel. So it is probably something close to 20 people overall. So I guess for Friday afternoon. Okay. Are we ready to get started? Okay. So in the hope that I can be heard, also over the internet, it is my pleasure to introduce the speaker for today's wide interest seminar. It is on Lattice Boltzmann method, and our guest is Travis Mitchell, coming from about as far away as possible on this planet, from Queensland. And he has been a collaborator with Marcus, who is a PhD student here, for 1.5 or 2 years, something like that.
Yeah, something like that. Yeah.
Something like that. And so since he's on coming to conferences here in Europe, we thought it is a good idea that he does a stopover at Surfax to renew and then to expand the contacts with Marcus, but also, of course, to show what he's been doing and to demonstrate what has come out of his, I think, mostly his PhD, right? So
PhD
your
today,
PhD,
yeah.
okay. So we're looking forward to your talk. So this is about Lattice Boltzmann methods, GPUs, and I guess in particular multi-phase flows. So very nicely aligned with the PhD defense that we had yesterday.
Yeah.
Travis, you have the word.
Thank you very much. I should also add that I was told to tell everyone that they can sign the form at the front and it counts for training of some sort. If you want some extra points and don't have to attend seminars later on. But yeah, apart from that, I'll jump into it. I'll just first off kind of show you, I guess where I'm from. And so yeah, I recently did my PhD at the University of Queensland, which is on the east coast of Australia. And it is quite a nice campus. So if you're ever down that way, feel free to drop me a message and I can show you around. I'm currently a postdoc there, and we'll see how that goes. And so I've been working there as a postdoc for the past 2 years on a variety of projects. And so I will just introduce kind of the projects that I'm working on, and then the main areas of interest for me. And then I'll talk a bit about two-phase flow and a little bit about the code base that we use. So the research motivations I have. So this is kind of, you do research either into what pays you or to what inspires you. And so at the moment, these are kind of the projects that I guess work on and fund my position. The top one is probably what I'm mostly going to be talking about today because it was quite related to my PhD. And that's looking at the flow inside of coal seam gas wellbores. So this is a two-phase flow scenario that's quite dynamic and has large density ratios that we're looking at. And so that's kind of the bottom image that you'll see here. So we'll kind of progress towards that as my talk goes on. But some of the other ones there, I just thought I'd highlight in case it does tick anyone's interests. I know you guys are a bit more aerospace, and our code has been applied to those types of applications as well. In particular, maybe not those applications, but in some of the similar difficulties that you might face would be in this bottom project where we have very low viscosity fluids and quite high, I guess, lattice velocities. But so those are kind of some of the projects that I'm on. But what my main area of interest is, as Uli said, is to multi-phase flows. And so I have a number of interests in this, both in multi-phase flows in, I guess, the natural world, as well as in industry. And so in industry for us in Australia, a lot of it's based around the energy industry. And so that's why a lot of my work kind of falls into the extraction of hydrocarbons or extraction of oil and gas. But yeah, so jumping into, I guess, some of the methods that we use. So the method that we're mainly known for, I guess, is the phase field method. And I will skip some of the Lattice Boltzmann basics because we had quite a nice introduction to that yesterday. And I will focus more on the phase field part of it, which is in resolution of an Allen-Kahn style equation. And so, yeah, I'll jump into that because it kind of has a bit of interest. And so effectively what we're doing is we're adding on to the Navier-Stokes equations another solver, which is the Allen-Kahn equation here. So our Navier-Stokes varies a little bit from probably the LBM that is used here in ProLB or in Wallavera, well, it's now in Wallavera as well. But we use this kind of incompressible formulation for Lattice Boltzmann, which means that our zeroth and first order moments are a little bit different than what you'd normally see. So we have a type of normalized pressure as our zeroth moment, and we have a velocity as our first order moment rather than momentum. And so what's nice about this is it kind of allows us to enforce the incompressibility condition a little bit more, rather than having this pseudo potential method. And that helps out a lot in terms of our pressure waves, the spurious pressure waves that ultimately generate instabilities for us. But so that's the hydrodynamic side of it. On the interface dynamics, so how we capture the boundary between our two fluids, that's kind of up to this equation here. And so I like to write it in this form, and it's not usually how it's introduced. So normally people will introduce this starting from a free energy functional and break that down. But I sort of like showing it like this because it really highlights, I guess, what the model is doing. And so what we have is an advection diffusion equation. But in our diffusion component, I have two terms. So I have, I guess, a diffusion flux and a separation or anti-separation flux. And so in the color gradient model that were introduced yesterday, those two stages happen separately. So they'll progress through, and then there'll be another stage that'll sharpen your interface. And so in Allen-Cartan style models, this is all done in one step. And so I'll show you how we kind of formulate these terms. So we start off with the diffusion term here, so JD. So you can see it's diffusing the interface around. And then we can think about this as wanting to reach some type of equilibrium profile across our interface. And typically for that, with Lattice Boltzmann methods, we use the diffuse interface method. So you want a rapidly changing function. And so often people use the hyperbolic tangent. And so if we take this as our equilibrium shape and we sub this into our diffusive flux, we're then able to derive what our anti-separation flux would have to be in. So if we sub this equilibrium into our JD term, we can then work to bring our original equilibrium profile. As you can see, it's really quite nice because it now tells us what our anti-separation flux would have to be to enforce this condition at equilibrium. So that's typically how I like to introduce the Allen-Cartan equation and how you kind of come to what you normally see in papers. And that's this full expression here where you have your diffusive term and then your sharpening term for your interface. And so I should note one problem here that I will touch on later, and I guess comes into a lot of multi-phase LBM, and that's in calculating gradients. So you do have now a rapidly changing region where you progress from your high density phase, in my case, to low density phase. And then you end up taking numerical derivatives of a hyperbolic tangent. And that's not always super friendly to do, especially when you're trying to do LBM style things. You want to keep everything as local as possible. But so that's how we kind of come up with the phase field equation that we're actually solving to capture the two phase effects. And then when it comes to discretizing the system, to solve that at the moment, what we do is we introduce another population onto our lattice. And so we've done this both in a Q15 lattice, and we've recently started using a Q27 a bit more because it helps with some of the numerical errors that we've been seeing. But what's kind of nice about it is that we simply just use an SRT method for the phase field. What we use for the hydrodynamics is actually a weighted multiple relaxation time. And so we had to move to this when we went into three-dimensional space. We tried just to propagate forward our normal multiple relaxation time collision kernel from 2D and had stability issues due to some unfavorable coupling of our higher order moments. And so we moved into this weighted MRT, and it's really been quite stable for us, which has been one of the quite nice aspects of the model, I suppose. And so going back to the point that I had that we're using this incompressible LBM. So the problem with that is that you actually resolve a momentum equation without pressure effectively. And so then you have to add these terms back in as source terms. And so it's maybe not quite as elegant, I guess, because you're adding these terms back in. But it's what we kind of had to do to ensure stability at these high density ratios by removing that pseudo compressibility. And what that ultimately means is that our total force down the bottom here is made up of a surface tension force. So dissimilar to the color gradient method where they apply the surface tension effects within their stress, so in their higher order moments, we simply apply it as a volumetric force along with our body force, our gravitational force, and then two different forces to bring back in the aspects we need to recover Navier-Stokes. And so that's kind of the discretization that we have. And then to the moments that we recover, so I touched on these before. So the main aspect that I'll bring up is actually down the bottom. So there's always the big question with diffuse interface methods is what are you going to do with your fluid properties in the diffuse interface? And so we played around a fair bit with this because there are ways that you can do it more accurately to recover more closely the sharp interface behavior in benchmark cases. But when you try and apply those methods into realistic simulations, suddenly everything falls apart. And so the balance that we came to was a simple linear interpolation for both the relaxation parameter, so that recovers our viscosity, and for our density component as well. And so I guess I'll just highlight a couple of the issues, because that's sort of a very brief summary of the method that we use. I'm more happy to go into details on that, but I guess the presentations maybe are the best for the hardcore details. But the additional points to keep in mind with these is, I guess, one of the key reasons that we developed this method initially, and that is locality. So we're using Lattice Boltzmann methods. We want high performance, otherwise, we have to resolve more refined grids usually than other methods, so we need that performance. And typically, two-phase methods in the phase field space have needed a larger stencil. So they've needed not only your nearest neighbors on your lattice, but also phase field values from external to that as well. And so then the other aspect of that, in keeping it local, is if we look at the derivatives that are required in this model, in some of these additional forcing terms, we actually require a velocity derivative. And so to remove that, we also recover these gradients locally using aspects of the LBM, so using the second order moment of our non-equilibrium. And that means our only remaining variable that's non-local is our phase field, and that we recover with simple isotropic differences, and like the Laplacian as well, from just our nearest neighborhood of points. So that's kind of the model. And now I kind of want to touch on the verification processes that we went through. So we did do quite a bit of verification. The main one I'm going to show you today is the Rayleigh-Taylor instability. We did see this yesterday, and it's typically used because it has a lot of complex aspects. You have very harsh interface deformations. You can push Reynolds numbers to be quite high, and it's been a pretty common benchmark in the literature for, I would say, the better part of the last 20 years. So the nice aspect of this is that we were able to apply this model to the further side simulation, and for those online, the one over here, to density ratios up to 1,000, with Reynolds numbers that other models that we had implemented couldn't achieve. So this was one of the nice aspects, and we were able to replicate that same behavior in 3D as well. And for anyone that's not familiar with this test case, it's effectively a heavy fluid sitting on top of a lighter fluid inside of a gravitational field. And so you have a very characteristic way in which the point here propagates down and the bubbles rise up, and people then use that to make sure they're consistent with other methods. One of the worser aspects, which we were talking about earlier today with some people, is that it's quite chaotic behavior that you have in the Kármán shedding turbulent, the more chaotic regions of the flow. And so those ones often differ a fair bit between models that you see. And isn't something that's often touched on in papers, but is something to be aware of, because it does indicate that the models are sometimes performing a bit different. But yeah, the main aspects they do look at are that characteristic propagation of the fronts. So this was one of the main verification tests that we used. We also did, of course, the Poiseuille flow and some deformation of droplets. But this one has the prettiest pictures, so it's the one that I always like to show. So that's kind of, I guess, an introduction and the verification. Now I want to talk about more of my PhD studies. So this is looking at long bubbles that eventually cause oscillatory flow in wellbores. Oscillatory flows cause pressure fluctuations. Pressure fluctuations, not good for fatigue, effectively. So this can cause damage to both equipment on the surface for hydrocarbon extraction, and it can also damage the reservoir as well. And so this is kind of where we took our peak point of interest. And as everyone does, we did start in 2D, just because you can do more computations. You can look at how different aspects of the fluid. So for us, we were particularly interested in surface tension at this point, how this affects the rate that these bubbles propagate at, and what kind of form they have in their wake region. So our first test case was a Taylor bubble. So that's what you see here with the low density and low viscosity, sitting inside of a stagnant fluid. And so then when you have a gravitational field, that bubble then rises due to buoyancy forces. And there was theory proposed earlier on that says that this scenario is purely dependent on your surface tension. So you should be able to predict your velocity, so your dimensionless velocity, based on the surface tension of that fluid in the scenario where your density ratio and viscosity ratio are high. And so this was what we wanted to recreate. And so this is kind of some of the initial simulations that we had from it. And so you can see the rate of rise. So Epvos number is kind of inversely proportional to surface tension. So higher Epvos number means a lower surface tension with respect to your inertial forces. And so you can see as that progresses through, you get this more chaotic behavior in the wake, and you get some really quite interesting dynamics where you get shedding of vorticity regions, and then eventually you get separation of the droplet itself into these satellite bubbles that then propagate with their own dynamics. And so there's some really like kind of fascinating just, I guess, inner fluid dynamics that goes on in these, which is quite nice to see. But ultimately, what we wanted to compare was the actual rate of rise of these droplets or these bubbles, because that was more applicable to the industry partners' work that we had. And so we were actually able to recover that really quite well. We did some, I guess, resolution testing on our time steps. So this is probably not the best in Lattice Boltzmann, because you should really do diffusive scaling if you're going to increase these things. But due to the computational restrictions we actually had at the time, we were working on a little bit less. We hadn't really delved into the HPC world. So this was quite a couple of years ago, I suppose. But we were actually able to recover that curve really quite nicely. So this gave us some pretty good confidence in the initial model that we were using, and kind of really kicked off the studies that we had. So shortly after this, we did get some compute time on some of the clusters in Australia, and that allowed us to rapidly propagate into 3D. And I'll also touch a bit later on the code that we use, and I guess why we were able to rapidly progress into this state. But yeah, so following the 2D work, we did some validation with an experimental group that were actually ejecting these bubbles into a case full of olive oil, which is quite a nice case to simulate, because olive oil, as you can imagine, is quite viscous. So you do have really high viscosity ratios, but you also have minimal separation of satellite bubbles. So it's actually quite stable and well behaved. And so once we did our validation on that, we then moved to what we were really interested in. And so with coal seam gas in Australia, you effectively have a gas and water flowing in these pipes. So they can be really quite violent flows. And so that was kind of what we wanted to propagate towards. So the other thing with coal seam gas is that they have annular piping configurations. So over on the side here is what we ended up using as our initialization of the domain. So you can see the red region, which is the gas bubble, and then it's through a liquid filled pipe. The shape there is a bit tailored for stability and initialization, because the minimal drag shape that you get for these bubbles in these pipes isn't an axisymmetric shape. You get a separation region where you have a channel, and then you also have water that flows out of your liquid film, so on the inside and the outside of that bubble. But our first piece of work in this space was looking at some experimental work from 1998, so it was quite a while ago. And they were only using 1-inch pipes, so quite small scale, really. But we did, in terms of stability, it was quite hard to push much bigger than that, especially with phase field models that aren't really designed for huge scales. But yeah, so this was the initial setup. So there's a 1-inch outer pipe and a 1-inch outer pipe and a 1/2-inch inner pipe. And then it's a water and gas, which is nice because they're actually realistic fluids that we're able to capture. And so this is kind of what the simulation looks like. So you can see that there's that breakdown of the liquid pipe. Sorry, I should show it on here for people online. The breakdown of the liquid bridge. And then you get, all your mass transport from your fluid going through that liquid bridge, as well as in the films of the side. And then you can almost just see them in the wake region, as you also get the separation of satellite bubbles due to the low surface tension that you tend to have between water and gas. And so this is quite nice because we actually end up with a very accurate match on not only the velocity of the experimental work, but also on the angle of wrap. So the amount of coverage that the inner pipe has by the Taylor bubble. And so this is quite nice because it indicated to us that we were not only capturing the macroscopic rise velocity of the bubble, but also its geometry as well. And so once we had this, we needed to extend and kind of make this applicable to the industry partners that we had. And so what they had is effectively a pressure gradient calculation that they wanted to do through their well. And what they didn't know is how fast these bubbles were going to propagate. And that kind of interacted into their larger scale modeling. So we end up doing a parameter sweep of a range of viscosities, which is this NF number here, which kind of correlates to each of these colored lines. So that's a variation in the viscosity and a variation in surface tension. And so with this parameter sweep, we had a whole range of data of how fast these bubbles would propagate in different fluids. And then looking back on literature, it seems like people generally fit these curves with power laws to two different regions. So a region that's heavily affected by the surface tension, and then a region that's relatively independent of it. And then in terms of matching these two different power law regions, people tend to use logistic dose curve fitting to balance those out. And so the nice part about this is that with the formula that we had here, we were able to kind of restrict the values of a lot of the fitting parameters. Because I guess when you're doing this kind of very empirical style fitting, you don't want these parameters to be super large or super small and kind of influence your simulation, influence your results quite rapidly in an unphysical way. So we were able to define effectively realistic bounds on most of the parameters based on the curves that we had seen. And so this was really quite nice and was then implemented into their software so that they could put in their fluid properties, and then they get the velocity of the bubbles that propagate, which then influences their pressure drop. And so that was kind of one of the nice outcomes of the PhD, was tying that in with the work that they were doing. But of course it didn't stop there, because that scenario that I showed you was quite basic, right? It's just a vertical pipe, concentric inner tube. Whereas if you're actually drilling a well out in the field, a lot of them are vertical, so a lot of them are straight, but a lot of them are also inclined or even horizontal. And it's quite rare that your central piping is going to be completely concentric. So we did look into those aspects for them. The one that I'll show here today in particular is the effective inclination, because this kind of has a nice kind of shape to it, because you can effectively pick the shape of the curve based on just rotating them all into the same plane. But effectively what you have when you have this inclination is you have the bubble now has not only a tendency to propagate up along the axis of the pipe, but now also to propagate radially. And so you get an elongation of the bubble as it's also forced to the top of the annular pipe region. And so this was kind of the main applications that I was interested in during my PhD. And yeah, post-PhD has now been incorporating the effects of this inclination as well as the effects of the inner pipe geometry into these closure relations for their larger scale pressure gradient simulation, pressure gradient predictions. So that's kind of the work for my PhD that I wanted to cover. And now I just wanted to touch on a couple of extensions that we're looking at. So a lot of the work we now do with two-phase flow is kind of moved from the connection of subsurface to surface to the subsurface. So this is looking at two-phase flow in fractures of complex geometries or porous media, as well as looking at the influence of fracturing fluids. So non-Newtonian fluids interacting with Newtonian fluids. And in particular, that's the application that I will touch on just now, just in a couple of slides to show where we're working towards. And so for non-Newtonian fluids, now we have our viscosity not only dependent on our relaxation parameter for LBM, but also dependent on the shear strain that we have in the system. And so typically this would require velocity gradients to calculate. And so again, we recover this locally in LBM, again, using that moment of our non-equilibrium function. But the problem that we now have is that, as you can see by this kind of collision operator here, for those familiar with LBM, S being the relaxation parameter is dependent on tau. And so if we have our shear strain dependent on tau and tau dependent on shear strain, we now have an implicit relation. And so in our code, what we do is just a fixed iterator solution. So we're boosting the number of, I guess, flops that we have to a region where we're now kind of potentially no longer memory bound, which isn't super ideal for our computations, but it's kind of what we require for the simulation. And so what we're dealing with in this case is Herschel-Bulkley fluids. And so Herschel-Bulkley fluids are kind of particularly interesting because they're not only non-Newtonian, but they also have a yield stress. So they need to reach a certain stress in the fluid before they actually act like a fluid. Otherwise, they're going to propagate as if it was a solid in the domain. And so this is work that we've kind of just started doing, and we've implemented into our code and coupled with the two-phase model. And so far, we've done a few verifications, including layered Poiseuille flow. And this one's particularly nice because you can see the unyielded region, so the region that's acting like a solid. And so it's able to capture that aspect. And we capture that with this regularized operation. So we don't actually have an on-off switch for fluid or solid, but it's just a rapidly changing function that allows us to operate in a bit more of a continuous fashion. And so the thing that I like about the non-Newtonian fluids is that you do get some really quite interesting dynamics that you wouldn't otherwise see. And sorry, this one's actually a droplet falling, not a bubble rise. But in this droplet fall, you actually get circulation regions just next to the Newtonian droplet that in the non-Newtonian fluid cause unyielded regions. And so this red circle here is actually a region of unyielded fluid that transports with the droplet. And so these are kind of really interesting dynamics that people see experimentally. And now with these types of models, we're able to kind of delve into why that is and actually analyze the shapes of the unyielded regions and how they operate with the bubble. So that's kind of, I guess, one of the areas that we're now looking into a bit more heavily. And then the other is back onto model development. So I showed this one, I think to Thomas earlier, because he was asking how do you calculate your gradients, because gradients are always an issue when you're recovering them in a relatively local sense for such, I guess, stiff shapes. And so one way that we're looking at doing that now is mapping our phase field, which is a hyperbolic tangent, to a linear function, calculating gradients of our linear function, and then feeding that back into our solution. And so you get a couple of nice aspects here, because now you're no longer propagating around the function that you're taking gradients of. So typically in these methods, your phase field for us goes between 0 and 1, but it might not always reach those upper bounds. It might be slightly above 1. And this is going to cause issues when you try and calculate these gradients. But if you map it to psi, say, which you're no longer streaming, you can cap psi without infecting the conservation of your actual equation. And so for us, that's quite nice because we're able to get more accurate predictions of what our gradient is. And we're able to cap the upper and lower bounds for those calculations without affecting the conservation of the scheme. So that's another area that we're looking into as well. And so that's kind of what I wanted to touch on the application side of things. And now I just wanted to introduce, I guess, a bit of the code and who we are that develop it. And I also want to touch a little bit on how we use code generation, because that's one of the aspects that I work with Marcus a fair bit. And I think we use in a similar way to enable rapid model development. And for us, it's to really enable a low barrier of entry to our code. We have a lot of honors students, so bachelor's students that do their thesis with us. And we want them to be able to pick up the code and not spend, the first 6 months of their thesis trying to learn the code and then the last 6 months trying to write it. We want them to be able to start straight away. And so I will touch a little bit on that as well. And so the group that I'm part of is led by Dr. Chris Leonardi on the side. And the code was initially started in Poland by Lucas. And so Lucas's main area was actually adjoint optimization. And so now the group has grown quite a bit. And I guess our overarching aim is really in that energy space. But yeah, so the code on top of what I've shown you today also has a large application in particle coupling. So with this fracturing fluids, you often send, I guess, small bits of sand underground as an easy way to think about it. And you want to try and capture how that sand's going to propagate through your reservoir and where it's going to get caught and whether it's going to stay there when you depressurize the system. So the code has a lot of capability in that space, as well as in the two-phase and complex flows that I've talked a little bit about today. But yeah, some of the main aspects that allow us to do these large-scale simulations is that we have tools specifically designed for code generation, which allow us to compile only what we need to compile. The code is very much CUDA optimized at the moment. We have got a project at the moment looking at, I guess, the next generation of AMD GPUs. So we now also use a HIP compiler for that, for anyone that does any bit more code development. And then I guess the third point here is the real, I guess, kind of key one, is the ease of defining new models. So at the moment, if you came along to TCLB and didn't have a model that you wanted, all you need to do would be to write effectively 2 files, and you'd be able to generate a new lattice Boltzmann scheme. And so that's kind of one of the key aspects. On the other side of it are a bit more computing related. So I guess the CUDA streams I'll show on the next slide. We effectively resolve our boundaries. Then we communicate our boundaries towards each other while we compute the inside of the domain, allowing for a little bit of additional parallelism there. And we have a single kernel. So the way that we operate is that we pull in all our densities to a single cell. We do all the operations on those, including the like the boundary formulations in a single kernel, which really helps for the readability, I think. Cool. And so this is I guess that's what I was talking about with the streams. So we have our boundary computation that goes around. We have our device to host communication. If we have MPI capable GPUs, we also have configuration options for that as well. And then we have, of course, the switcher buffers as per normal. And so I won't spend too much time on these ones because I guess there are some of the finer details. So this is kind of what you'd do if you are having a new model implemented. So we have effectively a lot of the communication and optimizations hidden inside of our source. And then inside of our model section, we have 3 files. So our .c file is effectively a pure C code where you can write how all of our different things, I guess our physics operates. And then all the parameters and things that we need are in the dynamics.r. And so then we use code generation to take any of the settings that we have in our .r file, flow those through .c, and then read those into the rest of the source code. And so it's really quite nice in that sense that you're able to, I guess, play around with the physics on one side, and then your code optimization is completely separate. And I will show a bit of an example as to how we actually implement those or how it looks from the user perspective. But before I do that, this is, I guess, our compilation strategy. So we have our model information, specific code in the .c file, and then our templates all inside of source. And we run a pre-compilation step where we've written a library called rtemplate that can execute in-place code in effectively any language. So either Python or R is typical, but we can also print strings in our code in place, which is really quite nice. And then we perform the compilation on that generated code. But yeah, so I guess for us, I guess the question people often ask is, why would you use code generation? And for us, it's relatively simple. So we don't really love C++ templates. We think they're a bit of a mess. So we use our R template as a bit of a wrapper in place to avoid those, which ultimately gives us a very readable code. We know exactly what's getting compiled into machine code and how that's gonna look and how it's gonna operate. Additionally, we use the code generation for optimization of structures. If you have a 2D or 3D vector, you want to compile one or the other. It allows us to do that on the fly. And the other context is a very LBM specific one, I think. But we do a lot of matrix multiplication if you're using MRT schemes. And so as you can tell by the name R template, we use R code for a lot of our stuff. And it has native matrix multiplication. And then we wrote a polyalgebra library, which eliminates any unnecessary calculations. So multiplying by -1, multiplying by 0, multiplying by 1 are all removed from the calculation to minimize the actual number of operations that you need. And so, yeah, why R? I have a few other reasons apart from the matrix multiplication, and that's its ease of embedding into files. So R, like C, is bracket orientated, whereas Python, for say, would be tab orientated for how you're going to align your code and how it's going to operate with if statements and this type of thing. Whereas with R, we're able to really like dynamically add it in for looping between different codes and stuff like this. And I'll just show you a quick example because I think it's the best way to sort of understand. So this is what a normal .c file might look like in TCLB. So you can see here we're creating a structure for a vector. And at the start, we've defined in R code some variable comp made of just a string of X and Y. And so the nice thing about this is you can see how linked it is into the actual source code. But when we run our pre-compilation stage, so we run this through our template, all this code is run, and we get our output over here on the right-hand side. And so this is only a very simple example, but I hope like you can kind of imagine how this would extend throughout the source code to a number of different applications where you want to have these loops where you have a mix of both your C code as well as your R or whatever language you want to use for your code generation. And so it's really quite nice. And I think this simple example highlights a lot of the positive aspects of it. And so then the other package that we use a lot is polyalgebra. And so this is the one that takes care of our operation minimizing. And yeah, so this will be the last little component of my talk before we can jump into some questions. And so with polyalgebra, I'll just show you a very quick example that takes into account this matrix multiplication and also shows what the C code looks like when it's printed out. And I've done this in R Markdown just to highlight that we do like R. But yeah, so effectively, we've got a couple of libraries in our code that'll just give me access for this example to my lattice discretizations and my lattice velocities and a calculation of my equilibrium. So if I grab my lattice velocities from my normal D2Q9, what I can then do is I can then generate my raw moments. If I look at my orthogonality being false. So what we do when we generate these is we always generate into raw moments of our Maxwell distribution first, and then we can just perform a simple transformation for any user-defined matrix. And so that's quite nice in itself. And then when it comes to actually generating, I guess, the C code, because we can do this native matrix multiplication, what we come out with at the end looks effectively like this. So this top line here does a nice matrix multiplication of our raw equilibrium with the inverse of our collision matrix, right? So we've got a solve of our equilibrium matrix. So it's the collision matrix, and solve finds the inverse. And then what's quite nice is we can then create PV as like a symbolic variable in SymPy. We can then simply create this vector of symbolic variables. And then using C here, we can assign one to the other. And so in the C code here, there's a couple of aspects that I would also like to point out. So what we do in polyalgebra is we pull out the highest common factor effectively. And so that's what you see in the 2 divided by 9, 3 over 18. And so divisions might not be great, but what we tend to rely on here is the compiler to take care of those. And we really focus on the printout being very user readable. So when you think about relating this to the equations that you normally see in papers, it's much more similar than if you had fractions and floating point decimals. And so that's kind of how we use it a lot inside of our dynamics.c file, and allows us to kind of rapidly generate these new Lattice Boltzmann models with different MRT matrices or different collision operators in general. Cool. So that's kind of, I guess, an overview of some of the research that I do, and I guess the tool that mainly enables that research. And so I guess with that, I'll kind of close off and open up to any questions, or we can have a discussion later on as well.
All right. Thanks very much for your interesting presentation. So the floor is open for discussion and questions, and also those connected remotely. Anything in particular?
Yeah, so the main reason is for avoiding the fourth order derivatives that you get in the Kahn-Hilliard. But the other thing that moved us away from it initially was there was a few people that had done studies where if you had droplets of certain sizes in Kahn-Hilliard, they would disappear. And so that, along with the difficulty of some of the terms, moved us more towards the conservative Allen-Kahn. But in terms of comparison of them, we haven't done too much ourselves. So I think that would also be like an interesting part for us to look at, because there are some times that you do see in the Allen-Kahn. I think Taylor Lee has been an advocate of it, of sometimes you see some slightly unphysical behaviors, but these tend to be very simulation dependent. And so a lot of the judge of the unphysicalness of these is also up for interpretation.
Surface tension. How do you tune surface tension?
How do we tune?
Tune the surface tension.
So in the Allen-Kahn, also in our model, the surface tension is defined explicitly. Yeah, explicitly defined and then incorporated as a body force that operates mainly over the interfacial region. So it gets multiplied by like a gradient of phi, which kind of localizes it in the regions where it needs to be applied. Which yeah, is one thing that we're also wanting to look into a little bit, because really it would be nice to include it in the stresses like they do in the color gradient model. And there was a recent publication as well that formulated it a bit different so that they could, yeah, apply it in these higher moments.
When the applied simulation,
Yeah.
you have any issue with the symmetry breaking down? So that is.
Yeah.
Any secure or adapt with the.
So yeah, so I mean, at the moment, it is a staircase approximation of it. But we have been doing work in the last, I guess, 3 months where we've been implementing a staircase improvement approximation. But with the bubble in particular, it tends to have like a liquid film around it, so it doesn't interact too directly in terms of like the three-phase contact. And we have relatively high resolution for it. So we thought it was going to be like quite a big problem, but we managed to kind of replicate into like a nice level of error with the experiments. So in that sense, we were kind of happy. But yeah, as we're going forward, we are implementing these like staircase improvements, and we haven't pulled it into our multi-phase stuff yet, but in all of our single phase stuff, we operate on interpolated bounce back. Yeah.
Just wonder, even if you use a Mesmer layering, you have some issue.
Yeah. Yeah, okay. So have you done ones in pipe before where they kind of match the staircase approximation too much?
So we just got some database for
Yeah.
we saw this.
Yeah. Were you doing it with did you have a full like Q27 lattice, or were you?
We tried with the Q7, yeah.
Okay.
It's good, but yeah.
Yeah, okay.
So you always use the coordinates.
Yeah.
With the 19.
So all the simulations I showed today were on Q15 for the Alan Kahn and Q27 for the hydrodynamics. And we've started using Q27 for the phase field as well a lot now. Just because for us, we haven't hit like, I mean, performance isn't like our main issue, and we haven't hit a limit where the compute time is unrestricted for us. But yeah, I think even Marcus has been testing the DT like lower dimensional lattices maybe, but we definitely see benefits in the Q27 in terms of eliminating some spurious behaviors in certain simulations.
And so my last question for me, just ask about so when you define synthi and
Yeah, so I mean they both operate pretty like in a very similar fashion. But we already had I guess the main author of the code initially used R. And so it was more natural for us to start off in that direction. And then we do see a few benefits because we have a lot of inline coupling, and R works quite nicely for inline coupling. But the polyalgebra library, which is our like symbolic algebra, is probably less sophisticated than SymPy. But because we wrote it, we also have access to like every part of it that we want to edit and things like this. But I think in terms of the difference between the two, it would just be more preference. Yeah.
All right, further questions or remarks? Also remotely, is there anything, anybody?
uniform meshes or if you're
Yeah, so our main branch is uniform mesh. We have an experimental branch that has like overlaid meshes, but typically we have uniform meshes for most of our simulations at the moment.
actually several levels of refinement?
No. We do have I guess like unstructured lattices, so we can remove our solid regions. But with our with the CUDA optimizations, we need a very high solid fraction to make it worth doing that. But yeah, for refinement, we don't do too much of it at all at the moment.
Maybe a meta question. Where does your collaboration with Marcus come in?
Yeah, so my collaboration with Marcus, so it started, I guess, just before COVID when you guys started using the Alan Kahn model.
So basically, I can also say a few words about it. So originally, we worked together with Matthias from Martin, my supervisor from the market leaders. And we have seen with the numerical model also that it was quite hard to have high density ratios, and also Halim went in more to a direction where he went to in-phase models and things like that, and it was just more in the sense of mathematical modeling was not so interesting for us. And so Martin basically, this was my master thesis, then has discovered here in Kahn formulation for the phase field model, and this was then my thesis to test this out and implement it. And basically for me, it was rather simple, so to say, to get high density ratio and high rate of number bases running. And it started in the collaboration when I got like problems, basically, and then I wrote, we started to write emails. And back then, what basically made the profits in both of us is that I had access to the Queensland supercomputer, which was the largest machine back then in Europe, which could be 100 GPUs. And so we did some scaling and large scale run of the phase field method, and then also when some of these pipe configurations in larger scales where we then have applications out of that. One vastly in the simulation performance techniques, and the other more like regarding physics, and also more in like different configurations, so different stencils and formulations for forces and things like that. Which we analyzed in a large equation set for in particular bubble cases. And at the moment, what we're doing is thermocapillary flows actually. So basically, when we have a temperature field in partition which is solved, so temperature equation, and then the surface tension is influenced by the temperature. And once again, so as long as you know, for me, it's mostly that I analyze the performance and that I do performance analysis in once, and I get the modeling part from Travis, and I think this is the quite natural way for me to collaborate to have like separation between the modeling and then the performance and analyzing of the communication.
Yeah.
And this is basically where the collaboration comes from and why we are here.
And I think the collaboration might really help us in particular with the refinement problems as well. So this week we just I guess corrected up the pull scheme that you have for the Alan Kahn model, so now it can be more directly coupled with the refinement that you have in Bolabira.
Yes, I could add answer here in this regard. So this basically I'm doing at the moment a PhD here in Surfax, which is mostly in the scalable context, which I get at least paid from. And the scalable project is in the end, of course, like Rayleigh and Valbala, to give a comparison. And so what Valbala has at the moment is strong GPU capabilities, but what it actually what it has not is mesh refinement on the GPU. So we're using mostly on the CPU. With the GPU, you get, of course, an aggressive performance boost if you can make use of the whole memory, of course, the bandwidth of the GPU, but you lose in the end drastic boost of performance if you cannot use the mesh refinement effectively. And so this is then quite natural for me to use to basically implement the mesh refinement in the code generation, that the interpolation schemes and things like that were generated. And this then again pulls back to the phase field models, because for phase field models it would be extremely important to have adaptive, not only static mesh refinement, because we really on the fly adaptive mesh refinement, and you need their very sophisticated and like rapidly changing meshes in this regards. And this, of course, is for me as a computer scientist extremely interesting because it's not simple. And as far as I see, I think the group around Naoki in Japan, they started at the moment quite strongly in the direction of adaptive measure fiber on GPUs with the block grids. So in these dimensions where we have our feed in. But the performance I see there is very nice for me because it's bad as far as I see it. And so I'm happy they're opposed to like up on this. But I guess the group there is strong. So I'm having, this makes me demotivated again because I know that it's not that I can say like, yeah, they're doing it wrong. So it's obvious what they're doing wrong. So it's quite hard. And I'm I'm very happy to work in this regard, but on the other side, it's really a hard challenge to board this in a way and to also have this in a way that it's not only functional in a sense of physics and so on, but also in a certain sense of performance.
Okay.
It's the context, and then this will add up again with the phase field because then all these techniques will be needed.
Okay. So that was kind of. That was now a long digression in that direction.
Again, the question also to the crowd in the background. Any other questions? Also, primarily, of course, for Travis and what he's doing. If not, I think we're at a good time to end 5 minutes before the full hour. Sounds good. So thanks again for coming and then for your nice presentation. And thanks to all of you that you have sacrificed part of your Friday afternoon. So hope it was interesting enough. And yeah, have a good afternoon, have a good weekend, and talk to you soon again.
Thank you.
So we try to get the doctor appointment now.